Right. Good morning, good afternoon, good evening, whatever it is for you, and welcome to what would have been, we'll call it lecture 28, on what would have been, we'll call it April 30th, 2020. So what's on deck today? Acids and bases. Basically what they are, what they do, and we will apply what we now know about equilibrium to them. To the learning objectives. All right, so by the time we're done with this set of videos, you're going to be able to write down the reactions that acids and bases have with water. You're going to be able to identify strong and weak acids and bases by their equilibrium constants. You're going to perform equilibrium calculations with acids and bases. You're going to be able to calculate pH. You'll know what pH is from hydronium concentration. You'll know what hydronium is, and vice versa. We're going to talk about polyatomic acids, what's in a buffer solution, and why they work. Tall order, but I have faith in y'all. All right. Acids and bases. So contrary to what the title might have you believe, there are actually two definitions of acids and bases that are commonly used. Now the first one is not my favorite except for the name, and this is the Arrhenius. So Arrhenius definition. Named after the Swedish chemist Svante Arrhenius, and I just like this because Svante is just a really fun name to say. Go ahead, give it a shot. All right. So in his system, acids are something that produce protons, and bases are something that produce hydroxide ions, and it is very important to know that both of these stipulate that water is the solvent in all of these. The Bronsted-Lowry definition is more in terms of behavior rather than the production of a specific chemical species, which makes it a little bit more general. So acids are proton donors. And bases are the opposite. They are proton acceptors, which makes acid-base reactions proton transfer reactions. All right, and before we go much further, I want to talk a little bit about when we talk about acidic species, what is actually in that beaker that you've got labeled acetic acid? The simplest case that we often talk about is that it's something called H+, but it is a solvated proton, H+ aqueous. Turns out that if you were to actually actively look in any acidic solution, you really don't find any H+ ions just floating around in there. What you actually find is have a proton that is interacting with a water molecule. Now, from what you know about intermolecular forces, this should make sense. A positively charged proton should be reasonably well attracted to the oxygen atom of a water molecule because of its relatively large partial negative charge. So this interaction is strong enough that we can actually almost call it a bond. And this species, which would have the formula H3O+, and has a name it is the hydronium ion. So basically it's water with a proton attached. Now it turns out that even that is not really correct, and that what you could also have is a proton that is interacting with not one water molecule, but maybe two of them. And this would have the formula of H5O2 plus. And there are some experiments that might lead us to believe that it's even more, it could be even more complicated than that a proton could actually have interactions with not one, not two, but three water molecules. And this species would have the formula H7O3 plus. And it turns out that these are tricky experiments to do, but what it most likely is a combination of the two, the H5O2 and the H7O3, with some amount of hydronium as well. But we actually stick with this one just because it's the simplest case that at least shows the fact that this is a proton that is kind of attached to or interacting very strongly with a water molecule. So hydronium, get used to it, you're going to see it a lot. All right, so let's look at some of this acid-base chemistry and try to describe it here. So I have a hypothetical reaction here. I have HF, aqueous, and it's going to react with aqueous carbonate. Actually, it'll be in equilibrium with that. And that's going to give us fluoride and either bicarbonate or hydrogen carbonate, whichever name you like. And those are both aqueous. So typically the first question I could ask you from this series is what's the acid and what's the base? And the answer from that really needs to come from the reactants, not the products. But to make the determination, you need to look at both the reactants and the products. And you want to kind of follow where the proton is, or where the proton went. And the easiest way to do that is you just compare formulas. So let's look at HF, right? So we have HF here and fluoride here. So what happened? The formula, we are down an H, and the charge has been lowered by 1. So this is the hallmark of losing a proton, losing a hydrogen plus ion. On the other hand, the carbonate went from CO3 2 minus to HCO3 minus. So it picked up an H in its formula, and the charge went up by 1. This is the hallmark of picking up a proton, an H plus. So this tells us that the proton transfer is going from the HF to the carbonate, which means that the HF is the acid and the carbonate is the base. So the HF is the proton donor and the CO3 is the proton acceptor. So let me give you one to work on here. So we're going to have aqueous HCN. It's going to react with aqueous sulfate, or be in equilibrium with HSO4 minus, or hydrogen sulfate, and CN minus, aqueous. And play the same game. Tell me what's the acid, tell me what's the base. All right, so by looking at the formulas, hopefully you determine that the proton went from went from HCN to the sulfate, which means that HCN is the acid and sulfate is the base. Now, let us kick this up a notch here. Pretend the reaction is actually now going in the reverse direction. So the HSO4 and the CN minus are the reactants, and the HCN and the SO4 are the products. And look at what was left of the acid. And tell me if that is acting as an acid or a base. So the part that's left of the acid is the cyanide, CN minus. Now, if you look at the reaction backwards, what is the cyanide doing? The cyanide starts as CN minus and it ends up as HCN. So it has actually picked up a proton. So in the reverse direction, what's left of the acid is actually acting as a base. Play the same game with what became of the base in the reverse direction. So we're looking at the HSO4. Now in the reverse direction, the HSO4 ends up as SO4 2-. So it gave up a proton, which means in the reverse direction, what the base became after it picked up the proton is now acting as an acid. And this is a thing. With any acid-base reaction, you will find that what's left over from the acid after it donates a proton ends up being kind of a base, and what the acid becomes after it takes the proton will end up acting as an acid. And as such, this is referred to as the conjugate acid. Can't write it in there fast enough. Or the conjugate base. I'll write it up here. So a conjugate acid-base or acid-base pair are two species that are related by the gain or loss of a proton. So HCN and CN minus are a conjugate acid-base pair, and HSO4 and SO4 2- are another conjugate acid-base pair. Now, one thing I could ask you, so let's draw a little separator line here, is now that you know what this is, I could give you a species and ask you what is its conjugate acid or what is its conjugate base. So, for example, from way back when, HNO3 was something that you should know as nitric acid. What is its conjugate base? And from there, you should be able just to say that, well, what happens? So how do you do this? What's the relationship? The conjugate base is what happens, what's left over from the acid after it donates the proton. So you want to remove an H from the formula, which would bring us down to NO3, and then reduce the charge by 1, which would take us from neutral to -1. And this is our friend nitrate. So let me give you another one. So a real popular base is hydroxide. This is the active ingredient in most cleaning supplies and Drano. What is its conjugate acid? Well, the way you would do this is simply add an H to the formula and increase the charge by 1. So that would bring us to O2H neutral, more commonly known as H2O or water. So water is the conjugate acid of the hydroxide ion. Right.